Okay, so let's start. What you see here and what we're going to use are some essential paths. So this is one of the exceptional graphs for SL3, for mathematics of SL3. And these are the essential paths. So let me start to describe what's going on. So first of all, oh, hello, 1, 2, 3. Did we lose it? No, it's all right. So first, let's do one thing about tensoring. You remember the multiplicities of a representation were computed with Hermann-Weil's formula. Hi, Zhengwei. Our colleague Zhengwei is studying teleportation, so he is now both in China and here. Now, you remember, as I said, the multiplicities, and let me put back the picture here. This was one. This was the adjoint representation of SL3, and this was the Weil alcove, Weil chamber, and no, this was the Weil chamber should contain one of these and very much in the middle. So the Weil chamber should be something like this. These were the generating weights, the fundamental weights, and what you had was the alternating Laplacian of Weil, which was something like plus minus plus minus plus minus. It generalizes the study of differences usually. So whenever you see equations with differences, so let me write here for SL2. This Weil alternating Laplacian is plus minus. So this is a difference. So whenever you see differences, the higher analog of that is the Weil alternating Laplacian, yes? And it had the property that when you apply to this, only these ones remained. So this one was with a plus, minus, plus, minus, plus, minus. So this was here delta alternating of the multiplicities. So these were the multiplicities. And this was delta alternating of the multiplicities. This is a Weil multiplicity formula. And now what we need one more ingredient here, the tensoring. So once again, with this you can very easily find the multiplicities. Yes, by inverting. If you have worked with things like partial differential equations, Also, this behaves very much like a Laplacian. This is a solution of, so delta alternating of multiplicities is equal to the sum over the Weil vector of W of e to the W of the highest plus rho, plus a Weil vector rho. This is a Weil vector rho here. And this, as I was saying, the Weil vector rho is a sum of all the fundamentals and is a difference between the additive origin and the multiplicative origin. Now, the tensoring, there's a very interesting formula. It was due to Rakach in the original classical case, and it is generalized to the quantum case. Namely, that if you want to tensor two irreducibles, alpha, beta, in the irreducibles of one of these simply algebras, G, then you can take alpha, then put here the multiplicities of beta. So you can take, these are the highest weights. Of sigma alpha and sigma beta. Now you take alpha as a vector, you write it multiplicatively to the alpha, you'll see why. The reason is that you may want to use things like 2 times alpha or so, which are not 2 times a vector, but the vector alpha taken twice. So we'll write this as e to the alpha, but this is alpha as vector. That's how we represent it. And these are the multiplicities of beta written multiplicatively. As exponentials. So you have here 1, in our case, 1, 1, 1, and 2 in the middle. Yes, and the also remember that this is the origin, and here you have the Weil vector rho, and you will have mirrors which will be located for SL3, something like this. So let me write them. So these are the mirrors, Weil mirrors. And now the result, so this is a result. So these are multiplicities. So the multiplicities of alpha tensor beta, of sigma alpha tensor sigma beta, are sigma of alpha plus x, where x is a multiplicity of, is a weight of sigma beta taken with multiplicity. And reflected with sign in the vial mirrors back to the vial chamber, or alcove in the quantum case. So here's what we mean. Is this part clear? So you see, these are the mirrors. This is a vial alcove, the vial chamber. Yes, so this is a vial chamber. The mirrors are at distance 1 from the walls of the vial chamber. Yes, because we add this vial vector, which is a sum of one fundamental weight in each direction. Yes? So imagine these mirrors now. If you have a, so you simply take one representation, take its multiplicities. If alpha was very big, then you just get the multiplicities of beta, yes? This is a formula which is very familiar to you from SL2. If you take sigma 10 tens sigma 2, yes? This would be equal to sigma 10 minus 2 plus sigma 10 plus 0 plus sigma 10 plus 2. Yes? Now let's write it the other way. Sigma 2 tens sigma 10, right? So this is sigma 8 plus sigma 10 plus sigma 12. And by the way, as you remember, this is also the multiplication law in case you need it for quantum numbers, right? So this is 11 times 3 is equal to 9 plus 11 plus 13, yes? And now, if you take sigma 2 tens sigma 10, and this is something that physicists are very familiar with, this is sigma, this would be sigma 2 minus 10 plus sigma 2 plus 10, yes? But here, sigma minus 8, so the mirror, the vial mirror is at sigma negative 1, which has quantum number 0 as dimension, yes? So sigma negative 1 is killed by the mirror, and the others are reflected. So this is sigma negative 8 plus, and so on, plus, let's put here sigma 8 plus sigma 10 plus sigma let's put, yes, sigma 8, sigma 10, and we should put here sigma 6, 8, 10, and sigma 12. Remember, the mirror is at sigma -1, not at sigma 0. So these two cancel, and the other cancel in pairs, yes, around sigma -1. And so you get exactly the same result. Yes, so you can see this thing holds in general for simple Lie groups. Now, suppose that we were at the, let's say, at the 12th root of unity. So we take now SL2 at n is equal to 12. In that case, sigma 11 is, which has dimension 12, is killed. This is a mirror. How do you explain the discrepancy again? Come on, fast. It's on the blackboard. Why is it this 11 and the other is 12? They differ? By? But what is at 1? Nope, it's on the blackboard. What is at 1? It's the, what fundamental thing? The 1, you know, it's the usual 1. And what is 1? The usual 1 is just like what we were mentioning. It's the difference between the unit for addition and the unit for multiplication. So this 1 here is what? The Weil vector rho. Yes, so the difference here is a Weil vector rho. Yes, so the Weil vector rho is 1 unit if we work with 2 times the spin, yes, or is 1/2 for spins, yes. So Weil vector rho, this is the multiplicative notation, and this one is the additive notation, yes, for the numbers. But remember that when you write the quantum numbers, what do? You exponentiate them, right? The sum of 2 exponentials, yes? So in fact, although this has never, in what I saw, been stressed, the representation theory of simple Lie groups is a continuous interplay between multiplicative and additive things, yes? And it has in its, at its very center, quantization. The quantization is an exponentiation, yes? So it has an exponentiation. It's the exponentiation between root written additively, like hij, yes? And the corresponding root written multiplicatively as the matrix unity ij, yes? And the theorem of Chevalet says that the EIJs, the commutator of EIJ with EKL is equal to 0, is equal to plus or minus EST if HIJ plus HKL is equal to HST. And this is 0, and there's the other case, which you can figure yourself. If they're the negative of each other, they're an HIJ. HST. If the sum is 0, HST, and then 0 if it's otherwise. Yes, so you see that the matrix units do multiplicatively what the roots hij do additively. Yes? The example here is that E12 commutator with E23 is equal to E13 because H12 plus H23 is equal to H13. This is commutative, so you cannot figure out the sign. Yes? And in general, when you build these things from scratch, that sign is a cocycle called the Euler cocycle. Now, let's look again here. If you have a mirror at sigma 11, in this case, sigma 12 would be equal to the negative of sigma 10, yes? So in this case, you'd have sigma 10 times sigma 2 is equal to sigma 8. Yes? Remark that in this case, which will be the case in general, if sigma 12 is sigma 10, so this is the additive 0 up to up to 12, yes? The sigmas multiplicative, this is 0, sigma 0, and this one would be sigma 10. So this is a graph is A11 in this case. And this is additive, multiplicative, and in this case, sigma 0 together with sigma 12, sigma 10, form a group Z mod 2. Yes? That center that appeared before in various guises. Yes, they have both the dimension of sigma 10. Notice that the dimension of sigma 10 is the dimension of sigma 10 is quantum 11, which is equal to quantum negative, which is equal to quantum 1, which is equal to 1. Yes, so the dimension is a sine function. Sine of k pi over n divided by sine of pi over n. So I'm writing them here because they have similar expressions in general. Yes? So this is how we tensor. And with this, so let me spend another minute mentioning the history of this. As you see, in principle, finding the multiplicities, there are different formulae. There's this manner of finding them is very seldom used in the literature as far as I could see. That's why I did it. Typically, there's a formula which is giving you the multiplicities on a line, on a one-dimensional line. Yes, and that's the one that's used line by line. And there's a constant formula, of course, which just counts a number of ways in which you can write a root as a sum of positive roots. But all of these, so the constant formula in particular, involve, so this formula for multiplicities for tensoring and for multiplicities is combinatorially subtractive. Which is bad. I mean, it means that it gives you the result as a sum with, of very big things with alternating signs. There is an additive formula which is which has for multiplicities you have the crystal, the canonical basis, the theory of Lustig, the equivalent theory of Kashiwara of crystal bases, some paths due to Littelmann, and for tensoring, and of course the Gelfand-Tsetlyn, which we have discussed. The multiplicative, for tensoring, there's the Littlewood-Richardson rule for the AN case. And the crystal bases also provide an additive theory, but this tensoring by Littlewood-Richardson, it was extremely hard to prove. So they were saying in the business that first man had to land on the moon, and only afterwards could they prove the Littlewood-Richardson formula. As to tensoring for quantum tensoring, this is unknown. At this point, an additive formula is not known. So the only formula use mirrors. There is an alternative formula. There's a Verlinde formula, which is a kind of Fourier transform. I have implemented in Mathematica because I needed them for this theory, both of them, the mirroring and the Verlinde formula. The Verlinde formula uses these Fourier coefficients, which are in a way even worse than having signs, but they can be very interesting if you do Galois theory, because they have some nice polynomials as a result. Now, as coefficients, let me continue. Well, once again, as you can see, this formula is quite adequate if we resign ourselves to using differences. And now we shall define the essential path And we'll work here over SL3, but with methods which work over any simple Lie algebra, and they extend immediately to semi-simple Lie algebras, for which this theory is just a product. Now, for the essential path, what do? We have a graph G, which, as was mentioned before, the algebra G acts on it. So we have tensoring on the graph G for alpha in the irreducibles or reducibles of the Lie algebra G. So here's an example. Oh, Arthur has appeared as well. As I was saying, both Arthur and Zheng Wei work on teleportation, so this is a great example of that. So now you take, let's take a very simple case here. We'll take just a graph AN. So let's put it in proper context now. These are the irreducibles of SL3. Here, this is the empty Young diagram. It will be worth if you, since we're going to a more and more crystallographic, towards more and more crystallographic things, to try to draw crystallographically. So make pictures which are accurate. So here you can see, remember that horizontally you have symmetric things, and vertically you have anti-symmetric things, and that each dot here is equal to V, which is C3. Yes, so these are things made of various, so this is made of 4 copies of C3, but our generators, the graph is A2, and the fundamental representations are V and V wedge 2, which is V bar, which you know very well. For the physicists, these are the representations 3 and 3 bar. And these are the reducibles of SL3 as written. And if you orient all the graphs here cyclically, all the vectors cyclically, basically you orient them like this, then this would be, this is a graph of sigma single dot tensor with any irreducible. So as you can see, basically if you tensor with sigma dot, what you will get is 3 neighbors. So this is sigma, which are what, according to what we were just discussing? These 3 are there. What do you get when you tensor? The formula is written on the blackboard. When you tensor with sigma alpha, with sigma beta, you get the multiplicities of beta, yes? So these are the multiplicities of of sigma dot. Remember that sigma dot is V, which is C3, yes? And these are the weights of E1, E2, E3, yes? These three. And so you can always, when you tensor with sigma dot, what you get is these three neighbors. And why do you have here only two neighbors? Come on, a little bit faster. And we have coffee. Now that Arthur is back, you can come a little bit early and get a coffee if you need before the course. So you can answer the questions fast. Where's the third one? Here. 1, 2. Where's the third one? In the mirror there. So these are the mirrors, yes? These are the Weil mirrors here, yes? And so here the third one is in the mirror, yes? And in the mirror it gets killed, yeah? The mirror should be right about here. Very good. So the other ones, you can use this graph backwards and get the multiplication, the tensoring with sigma bar. These tensoring with generators, because the quantum groups have a braiding for representations, which means that you get the same output when you tensor two things in one direction and in the other. So you don't quite commute, but almost. Now, the graph AN, I'm going to use the same picture here. If we put one more mirror here, and it's up to you very fast to compute what's the Coxeter number, the cutoff here. So if you put here a mirror, so this is a fine mirror. Yes, if you put the affine mirror here, then you have one more cutoff, right? And remember that the affine mirror is in the direction of is perpendicular to the affine roots. So the roots would be, do you see it's parallel to this one? And the roots, this would be so the roots are here, something like this. These are the roots for this picture. Yes, and they're perpendicular to the weights. Yes, so these weights were okay. Now, in this case, this is a graph AN, and there's a question about how to call it. We would call it the graph A3. This 3 is called a level, and physicists use a level as a highest degree not killed. Highest degree not killed by mirrors. Yes, so here you see this says degree 1, degree 2, degree 3, yes? And in this case, Coxeter for SL3, N is equal to the level L, capital L, N is equal to L plus 3, as you can see, yes? So here N is equal to 6. In this case, you can, so let me put here a few. This is L is equal to 1, so this is the AN series over SL3. L is equal to 2. The dimensions, L is equal to 0, excuse me. L is equal to 1. Here the dimensions are 1, 1, 1, and this is a group Z mod 3 at level 1 by tensoring, as you can see very easily by the graph. And L is equal to 2, we'll put here, and the dimensions are here 1, phi, 1 and phi. So phi is 1 plus root 5 over 2. And in this case, it should be quantum what? Remember, it's a quantum version of the classical thing, yes? Quantum? This was a representation 3 in physics, yes? So this is quantum 3. And here n is equal to 4. And this is quantum 3 at the 5th root of unity, yes? And finally, so exercise, compute the weights of that one. Yes, and check that they are. So you can see here that if you tensor with phi, this is a generator, you'll get 1 plus phi, yes? The usual equation for the golden ratio. And weights for L is equal to this is L is equal to 2, and weights for L is equal to 3, which is illustrated there. So again, the weights are coming from SL2. So the distance to the mirrors, if you have sigma and you have K single dots and L double dots, then the distance to mirrors is K plus 1, L plus 1, and K plus L plus 2. So the dimension is K plus 1, quantum K plus 1, quantum L plus 1, quantum K plus L plus 2, divided by 1, 1, 2. Yes? And in general, this doesn't simplify. So very good. And now let's compute on this AN graph the essential path. We'll take maybe let's take a moderately simple graph. So you see, if you tensor, we'll tensor with these representations. So you can see that the longest path in every direction is here has length 3, right, for that. So let's take this one, for instance, and well, why not the simplest of all, almost the simplest. L is equal to 1. We'll take this. We'll take some vertex, 1 at random. Let's take this one, A. And now we want to make a table, and at the same time we want to define the ribbon. And so this is a preparation so that the next time when we'll write formally the definition, it won't seem abstract. This is, so we'll have now the ribbon. Oh, actually, we can just define it. The ribbon, and this is the full ribbon, is defined as simply the Cartesian product between weights of G, weight, not weights, but weight, yeah, weights is fine, weight lattice of G, and these we'll call weights. Each of them is a weight of something. Weights lattice of G, Cartesian product with vertices of the graph G on which we act. Now, in the case AN, notice that for AN, G, the vertices of G are also weights. They are just in the fundamental alcove. That's how it is called. The chamber is a cone chamber, the vial chamber, and this is a vial alcove. It's cut off, and we should surround it by mirrors, always. So you see the vial alcove stays away, 1 unit away from the mirrors. Yes, everything on the mirrors is killed. And is killed by the numbers, by the dimension formula. So now we have this A, and let's consider now the tensor ring in the direction of the fundamental alcove. Now, when we did the ribbon, we had enough dimensions to make a nice Cartesian product, horizontal times vertical, yes? Here we'll just repeat one vector, one graph on top of the other, right? In order to do the Cartesian product. So let's do this. So now, if we tensor with sigma dot, well, you can see here the line. So what we'll have here is this. And what you will have here is this third one, or you can tensor backwards. You can go backwards. That's also a generator. So this here will be this. Yes. So it will have a 1 here, 1, 1, and the rest is 0 here. So here they are. See, everything is 0 on these mirrors. Let me make sure that the mirrors are the correct distance, which would be here something. So just try to reproduce the length. And what would happen beyond the mirror, just like for Alice, behind the mirror, what would you have here? Yes, yes. Any suggestion? Look at the whole theory. What is the number here? -1, exactly as here. Thank you, Filthy. So this is here a -1. Yes, all the rest are zeros. So this is 0 here, 0, 0, 0, 0. And we can put also one on the mirror here, just for show, and this would be, of course, 0, 0, 0, yes, on the mirror itself. And so these would be the essential. We don't have much in terms of essential path here. The essential path are edges from alpha, from A. Yes, and here you'd have a -1. Similarly, then you'd have a +1 again, and so on, and it will be periodic. There's another component of the full ribbon, yes. So here, the point is we don't take over Z mod 3. So this decomposes, the full ribbon decomposes into components if the graph is has a if G is K partite into K components, if it's K partite. In general, you can see this is it's a subgroup. It's for if you build compact Lie groups, you can build one which is like SU2. Remember that SU2 is a sphere S3 topologically, right? So you can build a Lie group which has fundamental group 1, yes? And you can build one which has fundamental group exactly that center that we discussed. There will be SO3 in the usual case. And you can have intermediate ones, in general, which correspond to various coverings of the one with a big fundamental group. But in this definition, for instance, this would give us 2 copies of the ribbon for SL2. We just use one. And we have arrived now basically at the end. I think in the last minute I should say that you can tense, if you have generator sigma dot and then sigma double dot, you tensor with this K times, and then with this L times, with this, so tensor, and you get a path this way. You can change the order of tensoring. We consider that the same path, but out of these paths, we have inside these, we have the essential paths, which correspond to tensoring with sigma with the irreducible, yes? K and then L. Yes, so you have the generators give you path, tensoring with the generators, and then out of those you can retain the path. You can project onto tensoring with the irreducible, which is the highest weight. So that's underlying our whole higher math, yes? And since we have built, based on that alone, we have built the representations of the higher theory, the usual theory actually for SL2, the ribbon, yes, was built entirely out of the theory of highest weight for representations of SL2. We can build similarly the theory for any simple or semi-simple Lie group. So you can do mathematics over any simple or semi-simple Lie group, and the mathematics done over SL3 and over SL4, in general, over that series should be viewed as the higher math in the sense of category theory. So So here, for higher categories, we go to from SL2 to SLN. Yes, but you can think of mathematics over E8 as something done as mathematics over A29. So it's a very high thing, but subject to extra symmetry. Yes, built-in extra symmetry. So we can do that as well. Yes, so in general, we can view these as higher math subject to some symmetry. We'll concentrate, of course, mostly on the AN case. Yes, and the theory will be non-associative, and so, but we'll build the actual representations and we'll extract the axioms out of those representations. And we'll try, the motivation is to build physics with it, so that's a very strong motivation to get the definitions right. And I'll stop here. By the way, we do have a mic. This one is okay, it was just not turned on, but we do have a microphone, and I have just talked to Jim Boyd, who will have this all the time for you. I explained to him that something that maybe karaoke singers know, that it takes time to get used to a microphone, yes? So it's much easier to just ask questions. So just try to get used to the idea that there's a mic, and if you speak into it, then your questions will be recorded by the camera. Otherwise not. Right, about?